Hello, welcome to MAT 223 Engineering Mathematics class. In this lecture, we will learn first order linear equations. The definition for linear equations was given earlier in this course, in the first lecture. We represent its definition for the first order case here for your convenience. If you remember, first order linear differential equation can be written in this form. So the derivative of y with respect to x times some coefficient function. This function can be at most a function of x, no y at all. And here we have y term and its coefficient again is a function of x and g of x on the right hand side. Okay, so the right hand side has to be a function of x alone as well. So the definition, another definition, if we divide both sides by the leading coefficient, so the coefficient of the first derivative, we end up with the standard form, and the standard form is given in this way. So a naught x divided by x1 a1x is p of x. We rename it, and it's p of x here and coefficient of y, and also g of x divided by a1x is equal to fx, and this is our standard form. Okay, so here we have a couple of examples. Okay, in this example we have the derivative of y, okay, and some function of x as its coefficient. So it is at most a function of x, so there is no problem with that. So there's nothing breaking linearity. Here also we have y, and x cubed is the coefficient of y, so it is a function of x, no problem at all. And also here another function of x, so this is a first order linear ODE. Okay, the second one, if you consider this one, we'll see sine of x dy dx, so this is the same, so no problem at all. And x cubed, again there's no problem at all. But here you see tangent x plus y, so y terms has to be alone here and with some x coefficients, and we cannot have the right hand side function dependent on y, so this is not a linear ODE. Okay, for the next one we have sine x times y, so this function, this derivative has to have at most a function of x as its coefficient, but here we have also y, so it breaks the linearity. Also, we also have y squared here. This is another problem. We have to have at most y there, right? So for if you compare it with the linear case, this also breaks the linearity. Okay, the next one we have sine x, and here dy dx squared. Okay, dy dx squared is also a problem because dy dx has to be alone, and if you rewrite it as dy dx times dy dx, then the coefficient of dy dx will be dy dx, so it will depend on y, so then we say this is not a linear equation. Also here we have instead of y we have the absolute value of y, so this is another problem. We have to have y alone here. Okay, so not the absolute value. This is also a problem, and this also breaks the linearity. Okay, so these are some examples, and all these last three were not linear, and the first one was linear. Okay, so since the first one is linear, we can talk about its standard form. The standard form for this particular case will be if we divide all the equation by sine x, then we will end up with dy dx plus x cubed divided by sine x equals tangent x plus 5 divided by sine x. Here the standard form, and this is the p function, p of x function. Okay, in the standard form, dy dx, the coefficient of dy dx has to be 1, so it has to be alone. Okay, solution algorithm. The solution algorithm for the first order linear ODE relies on the product rule for derivative. Let's consider the derivative of the following product. If we have, say, mu of x is some function of x, and we will try to find what this really has to be. Okay, so this mu of x times y is a function of x, and we can take the derivative of this function with respect to x. When we do that, we can apply the product rule here. So the derivative of y times mu plus derivative of mu times y will be the result for this derivative. Okay, the right hand side of the equation is somewhat similar to the standard form of the first order linear ODE multiplied by the function mu of x. Okay, so let us set them equal to each other and see what comes out. Okay, so the product is here, so this is rewritten here, and this product is equal to that. Okay, so this is already known from this part, and we say if this is equal to that. So if this is equal to mu times dy dx equals mu times pxy. Okay, this is the the right hand side of the standard form multiplied by some mu. Okay, so this is what's really happening. Okay, if you compare term by term, so we have mu times dy dx here and mu times dy dx there, so they're the same. Okay, so if we forget about these terms and compare these blue ones, we'll see the derivative of mu with respect to x times y is equal to mu times p of x times y. So if we set this is equal to that, then we basically have this the derivative of this product is equal to the right hand side multiplied by some mu function. Okay, and also this is from the equation, this part. Let's remove this and extend this rectangle a little bit, and this is basically equal to the ODE, original ODE itself. Okay, so this is original ODE multiplied by some mu. Okay, so if you can say, to rephrase it, if we can say, let's remove them. If you can say this is equal to that, if we can somehow show this is equal to that, this product is the derivative of this product is equal to that, then we can say the derivative of this product is equal to mu times fx. This is the main idea. Now the last equality holds if d mu dx times y, basically y will be eliminated because they're common term, it's common on both sides, so d mu dx is equal to mu times px. Okay, if this comes true, if this holds, then this whole equality will hold because the first terms are the same. Okay, we can solve this by separation of variables, parameters. Sorry. If we do separation of parameters, we'll see d mu over mu is equal to p of x dx, and here we have ln mu. Ln mu is equal to integral of p of x dx, and then if you solve this for mu, then this will be mu is equal to e to the integral p of x dx. Okay, so this is our mu function. This particular choice of mu of x is called as the integrating factor. Okay, now to summarize, if we choose mu is equal to that function e to the integral p of x dx, then we can say this is equal to that. Okay, so this will be very useful for solving the linear ODEs, the first order linear ODEs. Okay, next the algorithm. Given a first order linear ODE in this form, Put the linear first step is put the linear equation into its standard form, and this is our standard form. Okay, so this is the first step, and then identify p of x, which is there in the standard form, the coefficient of y, and then find the integrating factor by mu of x is equal to e to the integral p of x dx. Okay, when we do that, we will find the integration factor mu of x, and then multiply both sides of the equation, this standard form. You need to be careful here. Sometimes you confuse with the equations and multiply the original equation. No, when you find the integrating factor, it has to be multiplied by the standard form. Okay, so this is what you really need to multiply. Okay, when you do that, multiply both sides, you'll see on the right hand side, on the left hand side, you have d dx, the x derivative of integration factor times mu. This is from the last observation, so this has to be equal to that, right? So mu times integration factor times y. If you take the derivative of this guy, we have to end up with mu times f of x, which is here mu times f of x. Okay, so this equality will come out, and then here we can basically take the integral with respect to x in both sides, and you will have e to the integral p of x dx times y is equal to integral e to the p of x dx times f of x dx. Okay, when we take this integral and solve for y, we get the solution for the given first order linear ODE. Okay, let's see this process on an example. So this is the ODE, given first order ODE. Okay, we need to put this into the into its standard form. Then we need to divide all the equation by x. When we do that, we will end up with this dy over dy dx minus 4 over x y is equal to x to the fourth e to the x. Okay, then we need to identify p of x, which is negative 4 over x in this case, the coefficient of y. But you need to remember this negative here because it's also included. So p of x is equal to negative 4 over x, and then find the integrating factor by this formula here. Mu of x is equal to e to the p of x dx. Okay, we need to substitute p of x dx there, p of x in the last expression, so this will be e to the integral negative 4 over x dx. Okay, so when we take this integral, this is basically negative 4 ln x, ln absolute value x. Okay, so this is what's happening. Okay, so this negative 4, it's before the ln x, so the logarithm function, so this can be written as the power of the inside the log, so this will be the ln x to the negative 4. Okay, so e and ln functions are the inverses of each other, so they cancel out, we get e to the negative 4. So this is the absolute value is does not appear here because negative 4 power is even power, so x has to be positive or positive or 0. Okay, so we need to multiply both sides of the standard form. So this is our standard form. Okay, so we need to multiply the standard form, not the original equation. We need to be careful here. When we do that, we will see this the x to the negative 4 dy dx minus negative 4 x to the negative fifth, because negative 4 comes here and negative 1 here, we have x to the negative fifth y is equal to x to the negative 4 times x to the negative x to the fourth. They will cancel out and we will end up with e to the x. Okay, we multiply equation, this standard form, by the integration factor, and we ended up with this guy, and this is really equal to the derivative of x to the negative 4 times y is equal to e to the x. Why is that so? Because if you don't believe, just take the product rule and apply and see what's really happening. So the derivative of the derivative of second dy dx times the first x to the negative 4, and also the second times y times the derivative of the first guy. So this will be negative 4x to the negative fifth. So negative 4x to the negative fifth. This left hand side is really the left hand side of this last equation. Okay, so e to the x is common as this. So this is basically what we really have. So if we take the integral on both sides with respect to x, then we will see so this is the integral. We will see x to the negative 4y is equal to e to the x plus some constant, because this is e to the integral of e to the x is itself plus some constant of integration. And then if you solve this by for y, this means you need to multiply everything by x to the fourth power. Then we will end up with y is equal to x to the 4 e to the x plus c times x to the 4. This is our general solution for the ODE. Okay, singular points. Let's see this process on an example. If you solve x squared minus 4 times dy dx plus x plus 2 x plus y, sorry, x times y is equal to 0, the standard form of this equation will be this one. Okay, so we need to divide everything by x squared minus 4. When we do that, this will be our standard form. And then we observe that for x is equal to plus and minus 2, we see this p of x function is not defined and it's not continuous for this particular choice of x. Okay, so these points are problematic points for this differential equation, and let's see how this will be apparent on the solution. Okay, so if you find the integration factor, we need to take the we need to find e to the integral x divided by x squared minus 4 dx, and then this integral with substitution, if you say u is equal to x squared minus 4, then you will end up with this result for that integral. Okay, so this is basic calculus, and then this 1/2 power will go up on the natural log function. So negative 1/2 power is the square root. It means the square root. So inside it will we will end up with a square root of ln of a square root function. So ln and e are inverses of each other. So we will end up with this guy. Okay. To proceed, we restrict ourselves to this interval, because this has to be positive, so it can be positive for either this interval. If you choose this interval, you can basically eliminate the absolute value, or you can restrict yourself to the negative the open interval of negative 2 to 2. Okay, so we just choose this particular choice. Okay, when we do that, we can eliminate this absolute value, and we'll have this equation. If you multiply the standard form by this integration factor, it will be square root of x squared minus 4 times dy dx plus x divided by x squared minus 4, because x squared minus 4 here, if you multiply by its square root, then you will end up with x divided by the square root of that guy. Then it will be multiplied by y, and this will be equal to 0. And we know this is basically equal to the derivative of this product. So the integration factor times y. Okay, and this is equal to 0. If we take the integral on both sides, the integral of 0 is basically some constant, okay, c, and here we have root x squared minus 4 times y. If you solve for y, then you will end up with this solution. Okay, so this is the general solution. Okay, now let's see what's happening for x equals plus and minus 2. If you substitute that number, you'll see this function is not defined as well. Okay, so these points are called as singular points of the ODE, and this points causes some problems with the ODE, and we even had to separate the interval of the solution in the beginning, and then we solved that problem uh, on this interval, or either we could do the same for -2 to 2 interval as well. But again, these points are very crucial, and the solution changes its behavior on these points. Okay, and as you see, the solution has vertical asymptotes there, and again, it's not continuous there, and it's not defined there at all. So these are the singular points of the ODE. And also a similar fashion happens for the previous example as well. In the previous example, we had to divide everything by x. It means x is not equal to 0. Okay, x is not equal to 0. Then we proceed using this this assumption. Okay, so x to the -4, for example, is not defined for 0. Okay, so this will mean then we 1 over 0 to the 4th, and it's not defined. Okay, so in this particular case, x shouldn't be equal to 0. And this means if you again even with this assumption, we solve the problem and see y is equal to x to the 4 e to the x plus c x to the 4, and here in this particular case x is a singular point, but it doesn't cause a problem in the solution. Actually, we still need to be careful with this particular choice, and this x equals 0 will split our interval of solutions into two pieces, before 0 and after 0, but it's not apparent in the solution. Okay, so these are the singular points, and that concludes our lecture here. Thanks for watching this lecture. Bye.